Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about perpendicular and angle bisector theorems. To get started, let's look at the following problem that will lead us into today's topic. AP is equal to AQ and PB is equal to QB as shown in the diagram. Line segments AB and PQ are drawn such that they intersect at point N. If Pn is equal to 3z plus 4, AQ is equal to 7z minus 1, and NQ is equal to z plus 10, then what is the numerical value of PA? Now here, when we're referring to AP and AQ, PB, QB, and so on, we're actually referring to the distances between those points, or we can think of those as the length of those segments. So how do we solve this problem? Well, let's first write everything that we have into the diagram and then think how we can solve this. Well, it might be tempting to just set 3z plus 4 equal to z plus 10 and figure out the z value. The question is, can we do that? The answer is no, not yet, because we do not know if these two segments are equal yet. We don't know if Pn and NQ are equal. Now, if we look at the other givens, we know that segment PA and segment AQ are congruent, therefore equal in measure. We're also given that PB is equal to QB. Now, that is going to allow us to say that triangle APB is congruent to triangle AQB. How so? Well, we know that segment AB is congruent to itself because of the reflexive property. Now, why must that be true that triangle APB is congruent to triangle AQB? Simply because of the SSS postulate. Now that we know that these two triangles are congruent, we can now also say that their corresponding parts must be congruent as well. We could, for example, state that these two angles here must be congruent by corresponding parts of congruent triangles are congruent. So let's write this in. So here we have angle PBA is congruent to angle QBA because corresponding parts of congruent triangles are congruent. Well, how does this help us to determine that segment Pn and NQ are congruent? Well, there's nothing we can say yet because we first want to prove that triangle PBN is congruent to triangle QBN, and in this case we can now use the SAS postulate. First, we state that segment BN is congruent to itself again by the reflexive property, and then that triangle PBN is congruent to triangle QBN by the SAS postulate. Since the triangles are congruent, we can now say that Pn is equal to Qn because corresponding parts of congruent triangles are equal in measure. Notice that here I'm not writing that they're congruent, but that they're equal in measure. And the reason is because I want to simply substitute and want to figure out the value of z. Now, once we set those two expressions, 3z plus 4 equal to z plus 10 equal to each other, now we can solve for the value of z. Now, all we need to do here is just simple math, and we end up with the value of z to be equal to 3. Now that we have the value of z, we want to now substitute into the length from A to Q, which is 7z minus 1. So if we substitute into AQ equal to 7z minus 1, we obtain a value of AQ equal to 20. That's by the substitution postulate. And then we know that from the given that AP is equal to AQ, and therefore by the transitive property, we know that AP must be equal to 20. Now, in the very beginning of this problem, I had mentioned that it is very tempting to just set Pn and NQ equal to each other, or Pn and Qn, the way I labeled it. So it turns out that we can actually do that if we know specific conditions and criteria. Notice here that if we look at segment AB, what is the function of that segment compared to segment PQ? So let me quickly erase everything here so we have a better visual here. Okay, so we were given that this segment here, PB, was congruent to segment BQ, okay? So we know that this is also perpendicular. So it turns out that every time we have a scenario like this, every time we have a point here, and in this case, point B, that is the same distance away from the endpoints of this segment P and Q, and it's perpendicular to it, then it has to be true that in this case, this becomes the perpendicular bisector, okay? So let me write this in here, that this is now becomes the perpendicular bisector, okay? Which means that segment AB is not only perpendicular here at point N, but it bisects that segment into two congruent segments. So there's a theorem that we can introduce into this lesson. Instead of redoing this entire proof here over again, we can just simply use the theorem. If we are able to prove that and formulate the theorem, then we just use the theorem here instead of proving this entire thing here. And that's really how geometry works. Again, you want to prove something that is always true, formulate the theorem, and then use that theorem in subsequent proofs. It's like building blocks. So basically geometry is all about the postulational system and theorems where everything build upon each other. Okay, so at this point, let's develop a theorem that is always going to be true. So let's say that in this figure here, we have a point A such that it's equidistant from the endpoints of the segment BC, okay? So namely, we're given that AB is equal to AC. How do we prove that A is on the perpendicular bisector of segment BC? Well, first, let's create a statement reason table and write that AB is equal to AC. Now, how do we even prove this? How do we prove that A is on the perpendicular bisector of this line BC? Well, in this case, we need to first identify something specific or draw a specific point or a median or anything like that. And we can actually do that. Now, how do we prove this? Well, first, we can write that segment AB is congruent to segment AC by the definition of congruent angles. And then we can say that angle B is congruent to angle C. And the reason is, if two sides of a triangle are congruent, then the angles opposite those sides are congruent. Notice that here I had to change from measure to congruence because the theorem of this isosceles triangle uses the word congruent. Now, what else can we do at this point? It seems like that there's nothing much to do anymore. However, we can always draw additional points or lines if we need to prove something. Now, let's ask the following question. If we have a segment, in this case segment BC, are we allowed to draw a midpoint? The answer is yes. So let's say we draw point X, which is the midpoint of segment BX, which is the midpoint of segment BC. So what will be the reason in this case? Well, if we write that we want to draw X such that X is the midpoint of segment BC, the reason would be, given a segment, there's one and only one midpoint on that segment. So let's say we're connecting points A and X to draw segment AX, as shown in the figure here. Then what is the function of that? Well, we know that that is now the median of the triangle, but we actually don't need that here yet, but we're going to need it to prove the triangle is congruent in a bit. So let's first use the fact that X is the midpoint to state that segment BX is congruent to segment CX, and that we know is the definition of a midpoint. Now, can we prove the triangle is congruent? Well, yes, we can do it using the SAS postulate. Okay, so how does that help us? Well, we know that at this point, since both triangles are congruent, then it must be true that these two corresponding parts or angles are congruent as well. So let's write that in. So angle AXB is congruent to angle AXC because corresponding parts of congruent triangles are congruent. So let's think about this now. Here we have segment BC and segment AX intersecting at X. And we know that the adjacent angles are congruent. So what must be true at this point? Well, it must be true that those two lines now are perpendicular, because you cannot have two lines intersecting where the adjacent angles are congruent and not being perpendicular. So let's write that in. So here we can write that segment BC is perpendicular to line AX, because if two lines intersect to create congruent adjacent angles, then those two lines are perpendicular. Notice that here I'm not saying segment BC is perpendicular to segment AX, but line AX. Why am I saying this? Because it turns out that it doesn't matter where A lies. If we, for example, extended that segment to make a line out of it, then it doesn't matter where A lies, as I mentioned before. So for example, you can put point A over here. Well, guess what? In this case, that point A is still going to be equidistant and on the perpendicular bisector, as you can see here in the figure. You can also place A lower. If it's still equidistant to B and C, it's still going to lie on the perpendicular bisector. So hence, the last step on the proof is A is on the perpendicular bisector of segment BC. Why do we know that? Well, we know it's the bisector because we actually proved it here, right? We know that it divides the segment into two congruent segments, and we know it's perpendicular because we have proven it here. So the reason is the definition of perpendicular bisector. Now that we have proven this, we can finally formulate a theorem. So the theorem goes as follows. If a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment. So we could have used this in the do now, because if we go back to the do now here, we knew that point B is equidistant from P and Q, from those endpoints of that segment PQ. But we also know that it's already perpendicular at this point N. So must it be true that B lies on the perpendicular bisector of segment PQ? And the answer is yes, because we have proven it and formulated the theorem. So we could just simply skip all the steps here that I circled here and gone straight to the fact that these must be equal. Now that we have formulated the conditional of that theorem, which is if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment, and we think about it as the conditional statement if P then Q, is the converse true as well, if Q then P? Well, let's first formulate it. So the converse would be if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of a segment. So that's what we want to check. We want to see if this is true as well. So let's put a question mark. Let's first draw it out and see if we can prove it. So let's say that here we have the following diagram. We know that point A lies on the perpendicular bisector of that segment. So the question is A also equidistant to B and C? Well, let's prove it. Now, in proving this, first we want to write out what is given and what we're trying to prove here. So the given is usually the hypothesis. A point lies on the perpendicular bisector of the segment. So here we can write that line AX is the perpendicular bisector of segment BC. Well, what are we trying to prove here? The conclusion. The point is equidistant from the endpoints of the segment. So that means that we want to prove segment AB is congruent to segment AC. So let's look at this a little closer. So how do we prove this? We know that this is the perpendicular bisector, so we know that this segment is congruent to segment XC. So here we know that segment BX is congruent to segment CX. Well, we know that this is perpendicular at this point, so that means that these two angles are congruent. Well, we also know that this segment here, segment AX, is congruent to itself. So if we look at these two triangles here, we have a side that is congruent to a side of the other triangle, an angle that is congruent to an angle of the other triangle and another side congruent to a side of this triangle. So in this case, now we know that triangle ABX must be congruent to triangle ACX. And the reason is the SAS postulate. So what can we say at this point? Well, at this point, we can now state that segment AB must be congruent to segment AC. And what's the reason for that? Because of corresponding parts of congruent triangles, so I'm going to abbreviate it here, are congruent. Okay? And there you go, we proved it. So this was a very simple proof. So now we know that this is always true. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of a segment. So we're done with proving this particular theorem. So here we're just introduced two theorems pertaining to a point lying on a perpendicular bisector or equidistant from a segment. But the question is, does this also work for angles? Let's look at those. Can we formulate two theorems similar to the previous theorems pertaining to angles, referred to the following diagram? Let's think about this. The first theorem that we introduced previously was that if a point P was equidistant to the endpoints of a segment, then the point was on the perpendicular bisector of the segment. So this is now very similar. So we could say here, for example, that if a point is not equidistant from the side of a segment, or from the endpoints of a segment, but from the sides of the angle itself, okay? Then the point must lie not on the perpendicular bisector, but on the angle bisector. So let's write it out. So here's the proposal for the first conditional statement. If a point is equidistant from the sides of an angle, then the point lies on the bisector of an angle. What about the converse of the statement? So let's write it out. If a point lies on the bisector of an angle, then the point is equidistant from the sides of an angle. The question is it always true or not? Let's first look at the first proposal. If a point is equidistant from the side of an angle, then the point lies on the bisector of an angle. Our givens here are that segment PX is perpendicular to segment or ray BA, and that segment PY is perpendicular to ray BC. Why do we know that they're perpendicular? Well, because here we're saying equidistant. Remember that the word distant implies perpendicularity. So if you have a point and a line, the distance is always measured as the shortest path or perpendicular to the line. So given the fact that they're perpendicular, we can now work on this. For example, we also know that PX and PY are equal in measure. So what can we say here? Well, we also know that PB is congruent to itself. So here we have a leg that is congruent to a leg over the other triangle. The hypotenuse is congruent to itself, and we have right triangles. So we can easily prove that triangle BXP is congruent to triangle BYP. And the reason is the HL theorem. Now, once we prove them congruent, then what else can we say? That by corresponding parts, these two angles are congruent. So basically that angle XBP must be congruent to angle YBP. By corresponding parts of congruent triangles are congruent. Now, since that is true, what can we say about ray BP? That has to be the bisector, or we can say that ray BP bisects angle ABC. And we know that is the definition of angle bisector, okay? So that's how we prove this. So now we know that that is true. How do we know if the converse is true? Well, let's look at that. So the converse of the statement is if a point lies on the bisector of an angle, then the point is equidistant from the side of the angle. So again, now we know that ray BZ bisects angle ABC, and we also know that P lies on ray BZ. We also know that here we have PX is perpendicular to ray BA and segment PY is perpendicular to ray BC. Again, because here we're talking about distance, right? Distance is always perpendicular by definition. How do we prove that PX and PY are equal in measure? Again, by proving the triangles to be congruent. So here we know that these two angles are congruent here. And we know that here we have two angles that are right angles and they're also congruent. Well, we know that segment BP is congruent to itself. So again, how do we know that triangle BXP is congruent to triangle BYP? Here we have the AAS theorem that justifies this proof. So once we know that these are congruent, then now we can say that segment PX is congruent to segment PY. Again, by corresponding parts of congruent triangles are congruent. And since we know that they're congruent, then we also know that these must be equal in measure. And that is the definition of congruent segments, okay? So we are basically done also with this proof. So we proved that the converse must be true as well. So let's summarize now what we have learned in today's lesson. So in today's lesson, we learned the following 4 theorems. Number 1, if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. The converse of that statement is if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment. Then pertaining to angles, we learned the following theorems. If a point lies on the bisector of an angle, then the point is equidistant from the side of an angle. And the converse of that is if a point is equidistant from the side of an angle, then the point lies on the bisector of the angle. Let's now look at a final example where we can apply any of these theorems that we have learned today. So according to the diagram, we know that segment SR is the perpendicular bisector of QT. And we also know that segment QR is the perpendicular bisector of segment PS. How do you prove that segment PQ is congruent to segment TS? Well, let's first generate a statement reason table and label whatever we know in the diagram. So if we write the first given, that segment SR is the perpendicular bisector of segment QT, what does that allow us to say? Well, we know that this point here, point S, let's mark it in the diagram, must be equidistant from the endpoint of the segment QT. Namely, we know that segment QS is congruent to segment ST or TS. So let's write that in. Segment QS congruent to segment TS because if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of a segment. Similarly, we can state that segment QR is the perpendicular bisector of segment PS because that's the given. So if we look in the diagram here, we can now state that if we have this to be the perpendicular bisector, that segment PQ must be also congruent to segment QS because it's equidistant. So we can say that segment PQ is congruent to segment QS because of the same exact reason as number 2. Now, if we look at step 2 and 4, what can we say here? Well, they both share the same segment QS. So therefore, we can say that segment PQ is congruent to segment TS by the transitive property. And that's basically it. So these theorems are very useful because they allow us to prove certain statements in a much shorter way, instead of proving all the triangles congruent and so on and so on. But that's basically it for today's lesson. I hope you enjoyed it. Again, thank you for watching and have a wonderful day.